Hi, welcome to the senior design presentation for the Smart Well Plate system. This project is with the Bliss Laboratory here at CSU, and our advisor is Dr. Thomas Chen. The Smart Well Plate system is divided up between 8 members in 5 sub-teams. Starting off with the mechanical team, we have Katie Wood, who is biomedical and electrical engineering. And then the electrical team consists of Kylie Mitsuyasu, who's computer engineering, and then Aaron Murphy and Ryan Way, who are both electrical engineering. Moving to the software team, we have Naji Faor, who is electrical engineering, and Yuming Liu, who is computer engineering. Then with the imaging team, that is Ryan Barnes, and he is in electrical engineering. And finally, we have myself with the laboratory testing team. I'm Katie Brown, and I'm studying biomedical and electrical engineering. And to the left, you can kind of see in our picture how all of the teams are integrated into the well plate system. The Smart Well Plate system is a bioanalytical system for measuring cell metabolism. This technology uses electrochemical sensors with the use of electronics alongside it. This system will measure key cell metabolites such as hydrogen peroxide, oxygen, and glucose. This system could be life-changing for diseases such as cancers, where there's very limited understanding of how cells respond to different drugs. And there's a current lack of real-time measurement of cell responses during the incubation period, which is 24 to 72 hours when the cell reacts with the drugs. And so the Smart Well Plate system is a technology that we hope will combat this problem that we have.
Smart well plate actually do this? Well, first off, we have our system sensor, which consists of 6 electrodes, 5 of which are made of gold with silver reference electrodes, and 1 of which is made of ITO, which is a clear metal for sensing pH. Now, this sensor is placed underneath a well that has an inlet and an outlet port and a view port on the top. And then this is placed into the Biobox, which is seen on the right here. Now, in the Biobox, a PCB that contains a potentiostat, which can measure the different readings they get off this electrode, is placed on top of it. And then the outside of the Biobox looks like this. Now, the mechanical portion of this project, you can imagine there's a lot of it. So first off, we have the well system here, which I discussed in the previous slide. So the well consists of LEDs that we can place in the sides. Then we have the chip that we adhere onto it with either epoxy resin or super glue. Then we have an O-ring, a glass cover slip, and then a twist top that comes down and then securely locks the system together. In addition to this well, we also have a microfluidic system, which is seen here. Now, this microfluidics system is for future uses that we're testing out right now. So in this, instead of having electrodes placed inside the well, all 5 of them there, we would spread out the electrodes in each individual spaces here. And we would push fluid through that microfluidic so it evenly distribute on each of those sensors. But each of those sensors would not be able to interact with the other ones because they would be in isolated chambers. Now, we also have a syringe pump mechanism. So the syringe pump seen on the right here can pump down to 1 microliter per minute. Accuracy is what we aim for. It can actually pump down less than that, but that was the goal. And with this syringe pump, we also made a GUI. Here you can see the front page of the GUI where you can enter a flow rate, start, stop, and reverse the syringe pump, all on a touchscreen that's attached to the syringe pump. It also records the temperature here, so we can vary the temperature of the syringe pump liquid that's in there, because cells usually like a very specific liquid to be happy.
Hi there, I'm Aaron, and this is the electrical sub-team. For our sub-team this semester, our work mostly consisted of soldering and debugging the boards that had already been printed. And so a lot of the work that our sub-team did this semester consisted of just going through and testing the boards chip by chip and making sure that we were getting the correct output and then getting them ready to run with the GUI. And so next here I'll hand you over to Ryan Way and he'll tell you about the instrumentation board.
Hello, my name is Ryan, and for this project I worked on the instrumentation board. The instrumentation board is one of 2 PCB boards that we have for this project, the other being the internal PCB. But the instrumentation board is the first connection that the electrical chemical sensor has. This board's job is supposed to retrieve the signal, perform amplification, send it to the GUI, and do other stuff along those lines. This semester, really been working on soldering it and testing the physical board. And so far, we've been able to actually successfully communicate with the GUI, and hopefully in the future we can put in an actual cell and get some readings. Next will be Kylie talking about the internal PCB.
Hello, my name is Kylie and I'm also on the electrical team. I've been working on this internal PCB, and once that was completed, I also moved on to helping Ryan and Aaron finish their tasks and boards as well. The internal PCB mainly focuses on logistical aspects of the Biobox. It has a stepper motor to move the stage of the Biobox, and it also includes LEDs and push buttons for user interface. It contains things that the instrumentation board needs, like a power supply, and also has heat sensors so that we can regulate the temperature within the box environment and ensure that the cells can survive. This board is completed and is currently with the software team to make sure that the board works and that the GUI can control the stepper motor and other functional things of the internal PCB.
Hello, I'm Yiming, and I'll be presenting the software portion of the project with Neji. So the basic goals of this portion is to provide a usable and effective GUI for the user, and to also be able to easily configure and change settings for hardware and software through the GUI, and also to provide easy to understand data and plots for the user. For the general UI, the basic layout was that there was multi-well options such as single, 6, 12, and 24-well options, as well as media sensor load, run, and results tab underneath to configure settings and show results. For file I/O, basically what happened was for the save and apply buttons, you can save and apply settings for media and sensor settings. And then also in the load tab, there was a load and unload procedure associated with it that was used to load the chip onto the board or unload the chip onto the board. The general data structure that was used was a general system settings followed by different wells, and then sensors underneath that, and then specific settings for those sensors underneath that as well. I'll pass it on to Neji.
Hello, my name is Neji, and I worked on the software part of the project. Specifically, I worked on the plotting UI, which has a few different features, such as you can change the color of the plots, you can save the plotted data, and you can also change the names of the plot or the curves themselves. Part of also my job was to get signals from the FTDI on the electrical board to the computer, so that interface. So I programmed the software to communicate with the FTDI and request data in different protocols. Specifically, I worked on the SPI protocol. So now we can actually plot real-time data received from the FTDI to the plot. Next up, we have Ryan Barnes with image processing.
In order to visually see the cell response as it happens, we are using the Biobox's microscope system. The Biobox is a self-contained environment control system that was developed as a previous senior design project. The first program that was implemented was an autofocusing program. The autofocus program used information about the type of equipment being used in the Biobox to determine the range of focus. The second imaging tool I implemented is an image stitching program. This allows us to take multiple detailed pictures of sections of a well and stitch them together to create a complete image of a single well. The final imaging tool I created is a time-lapse program. This program allows the user to choose what type of equipment they are using and which wells they wish to image. Future development of this program will include using the image stitching program, allowing for stitched time-lapse images.
The laboratory testing that has been conducted through the senior design team this year has included hydrogen peroxide, glucose, and oxygen testing. These are calibrations, and for these calibrations and all other experiments so far, we have used PalmSense 4, which is a potentiostat, meaning that it provides a voltage to the system and we read the output of current from our system. And so here you can see our electrode design, which is in the top right corner, which changed partway through the semester because we wanted a higher electrode surface of the counter electrode in order to gain a higher sensitivity for metabolite sensing. And so once we changed the electrode size, we went back to working in calibrations and oxygen consumption rates with bovine cells from our collaborators. And here you can see the new electrode design, like I mentioned. Down in the bottom right corner, you can see the new well design. In the top middle, you can see the equipment setup that we have so far, and then on the top left, you can see an example of our oxygen consumption rate, and that's of 20,000 cell densities of stem cells that we ran with our collaborator at the Translational Medicine Institute. So that's the testing that has gone on so far, since we have not integrated our system yet.
This project will continue for future years, and for the team that comes in to take over on this project next year, their first task will be continuing the integration that we've started this semester of the various hardware and software components, and also of the mechanical system, the microfluidic wells, the digital imaging system, as well as collaborating with the laboratories that we work with. Now, for future plans on this project, a big thing that is expected is progressing to a 6-well system. So this system that we talked about in this presentation, the instrumentation board centers around 1 well, and there's some design work in place, especially on the electrical team, for moving forward to a 6-well system where there'll be an instrumentation board sitting around 6 microfluidic wells so that they can be compared. And so in conclusion, we'd like to say thank you to Dr. Chen, to the graduate students Ming Hao, Michael, Jacob, and Daniel, and to all of you for watching this video. Thanks for your time.